And for a confidence interval for a difference of proportions, we have a standard error formula, very slightly different from the standard error formula for a hypothesis test. We have the two different sample proportions showing up in this standard error formula. There's really no such thing as a null hypothesis when we are finding a confidence interval, and so the idea of using a pooled proportion doesn't come up here. We just look at the two individual sample proportions and put them into this standard error calculator, but we are not responsible for it. We can use a visualize applet with the link in Blackboard on homework, and on tests the standard error will be provided. So we will see how we use that visualize applet as we get into this next example. A confidence interval for P1 minus P2 starts with the sample statistic, which is going to be P1 hat minus P2 hat, and then we add and subtract the margin of error, and the margin of error looks an awful lot like the margin of error for a confidence interval for one proportion. Margin of error is equal to Z star times the standard error. The only real difference is that now our standard error comes from this formula here. So we have a different formula for standard error, but based on standard error, still the same way of calculating our margin of error. So we're going to estimate the difference in the proportion of successful pregnancies between all smoking and non-smoking women using 90% confidence. First, we have our sample statistic, PS hat minus PN hat, which we have already calculated at negative 0.098. To get our margin of error, we're going to need a standard error, which we can go ahead and get from Blackboard now. Coming to section 6.3, we see this link to the standard error applet. And here I'm going to enter those same values that we did for the hypothesis test, 38 out of 135, and 206 out of 543. But this time I'm going to select confidence interval instead of hypothesis test and compute the standard error. We can see we get a number that's very close but slightly different. 0.04395. And based on this and my Z star for a 90% confidence interval, we either have these memorized by now or can look them up in table A. That's going to be 1.645. So table A is where we would go to look this up if we didn't remember it. Or looking even at our notes for one proportion would also work. So I'll calculate my margin of error based on that Z star and standard error by just multiplying them together. And this gets me 0.0723. In my first calculation of margin of error, I usually take it out a little bit further than I think I need to. When I'm actually finding the confidence interval, that's when I decide how far to carry that out. So my confidence interval is my sample statistic plus or minus my margin of error, which is negative 0.098. And my margin of error, I generally take either the same number of digits or one digit further if it happens to be very small. Since it's not very small relative to my sample statistic, I'll go ahead and take it out to the same number of digits. So I'll cut it off here at 0.072. And that subtracting to get our lower bound gets me negative 0.17. And then adding to get our upper bound gets me negative 0.026. So this is our estimate for the difference of proportion. When we go to interpret this confidence interval, we want to think about which proportion is larger, since we subtracted as p sub s hat minus p sub n hat, and we got an interval that's all negative. The interval being all negative suggests that Pn is actually the one that is larger than Ps. So we want to say that the proportion of successful pregnancies is between 2.6% and 17% lower among smoking women than among non-smoking women, or we could say higher among non-smoking women than among smoking women. Since the values were negative and smoking came first, I chose to do a little bit more direct interpretation and use the word lower, stating smoking first and non-smoking second. But it works to write it in the other order, also using the word higher. Do make sure that your interpretation makes it clear which one is higher than the other. We don't just want to say that the difference is somewhere between these two values and leave it vague. That's kind of like saying that a World Cup game ended with a score of 5-2 and not saying who won, right? It's certainly interesting information that the score was 5-2, but it would be a whole lot more interesting if we knew who won the game.